Hello, in this lesson we are going to cover topic 2.9, also known as further modeling. So we are going to cover all sorts of different models that you haven't learned before. Then we're going to deal with one exam exercise, and then furthermore we are going to just do some exercises to actually understand if you understand. So exponential model of half-life is the first one that you have. You might be wondering, what the hell is this? Well, essentially exponential model of half-life could be if something is going exponentially up. And I think examples of this could be like bacteria. As you know that if bacteria usually multiplies, bacteria's growth is also known as an exponential function. Why? Because if you have one bacteria and it goes to one other bacteria, and then this infects other bacteria, therefore it's like an exponential disease in this case. However, if it's the opposite and your exponential function is decreasing, as you can see here is a minus, then this can be something like a radioactive material. Why? Because radioactive material usually decays. However, it doesn't have to be radioactive material as well. It just have to be material that decays. And you're given this function. So A is the mass of your radioactive material. So A, let's say, is the material, and T is the time, and your lambda is your decay rate, and furthermore your A0 is your original amount. So I think to better understand this, let's actually look at our graph. So you have your time to be this x, and your material is here, A, and A is usually in grams as well. And then you look at your material. Let's say that you see that here your material is 300 grams, and you can tell that in that time it is about, let's say, 7 years. However, as your material decays, as you usually know, radioactive material, it like disappears over time. And if you have radioactive material, it decreases and decays in an exponential function model. So after like 20 years, let's use years, your function is over here. And after 20 years, you have a new value for your radioactive material, which is here. This might seem a little bit complicated. However, you really have to just understand that A is your radioactive material, and that means you can check the graph. How much material do you have left? How much material do you have left at any time frame? So of course, after 0 years it hasn't decayed anything. However, in this case, in 40 years it has almost decayed fully into the original amount. So the half-life formula is also something that you have to know. So when we look at our function, I'm gonna sketch out the function over here as well. So your function usually, when you're looking at decay, looks something like this. So you're wondering, what is the half-life formula? So let's say that your material is 100 grams. This is your A, and it's 100 grams, and the half-life formula means that you're searching for, let's put 1 and 2, you're searching when your half-life, meaning that when is your when is the weight of your material actually half of this. So you're searching for the time that when the material has become from the maximum to half, and usually it's somewhere here. So let's do an exercise as well. And before we do that exercise, I want you to print this formula, maybe onto your wall, maybe onto your laptop, and the formula is equal that the half-life, you're searching for the T. So when you're searching for your 50 grams in this case, you're searching when is 50 grams. And you're searching for the time. And so it is a natural logarithm of 1/2 divided by the decay rate. So let's do an exercise as well. This is a quite difficult exercise, so then I hope you can follow. So you're given, after 200 years, a sample of tungsten 556 has decayed to 74% of its original mass. Find the half-life of tungsten 556. So if you have your function and you have your tungsten, you know it's falling in an exponential rate, and then you want to know that when is the tungsten value exactly in the middle. So over here. So you go back to your first formula, and you know your first formula was A is equal to, let's check it again, A0 times E to the power of negative lambda T. So now you can dump your info in. So as you can see, you have your, it says that after 200 years, a sample has decayed to 74% of its original mass. Therefore, you can multiply, because what is A? A is basically a certain spot in here, and it said that after 200 years, let's say that 200 is somewhere here, so we got this from here, from the text, that it has decayed to 74% of its original mass. And then you can really kind of bring out that 74%, also known as 0.74 of A0, and is equal to A0 times E to the power of negative lambda times 200. So you're wondering, how did I get from A to 0.74 A0? Well, essentially it's just, if it says that it has decayed to 74% of its original mass. So think of the sentence, 74% of its original mass. So you can kinda make this, because it said that after 200 years, it has to decay to 74% of A0, because it's, and then you can write it out as 0.74 A0. Then you use simple algebra. You know that you can cross them off. Then you get 0.74 is equal to E times lambda 200. And then you should know how to use your numerical solver. You go to 0.74 is equal to E to the power of, I'm just going to put negative 200x. Then you're going to solve alpha, and then you're going to get a very small x, obviously. And of course it's going to solve for lambda. So as you replace lambda with x, and then you're going to get lambda is 001 50552. I don't think I need to write more. And then, because it said that find the half-life of tungsten 556, then you're going to use the formula that I told you to imprint in your brain, and then you're going to get the half-life of tungsten 556, I'm sorry, is equal to natural logarithm of 1/2 divided by negative and whatever this number, I'm going to write it all out, and then you simply go to your calculator. Then you will get your natural logarithm of 1/2, and then you're going to divide it by negative 150,552, and you're going to get your answer of the half-life to be 460, and this will be in years. Why is it in years? Because after 200 years, then you will always have to use this as years as well. This is definitely an exercise that is actually quite difficult. Usually you're just given you're given a mass and then a time. It's like at 50 years the mass is 30 grams, and then you can switch the A here and it will be much more easy. I hope you can understand. You will have like 30 years and 10 grams, and then you just replace 10 and 50 over here, and then you will get a very simple equation. So this is something very difficult, but it's always good to learn the difficult exercises as well. So let's learn the logarithmic models as well. So logarithmic models, we are not going to go into much depth right now. However, you always have to know with logarithmic models is that their shape is usually something like this. So it goes something like this, and it has all sorts. I think you can look at examples online. However, we will have in future topics, we will go into more depth in this as well, so you don't need to stress out as much right now. And something very important that you have to know with logarithmic functions is that you have your calculator, and usually you're given data. What this means is that you're given slots, and the slots are filled with x and let's say log y, and you have your data all over, and and then you just go to stat calc, and you see there's two types of reg. There is a natural logarithm reg. This is if you have natural logarithm, and then you also have logistic reg. This is for logistic functions. So sinusoidal functions is something that we're going to go more into depth in this lesson as well. So I hope you can cover and remember from my previous lesson some of these things, and then we'll do an XM exercise as well. So amplitude is just the true value of A. So your period is usually your B, and the formula for B is also the period divided by 2p, and this is if you're dealing with radians only. Then the axis is the D. This kind of like if you have your function like sinusoidal function, and it looks and it looks something like this, and you can clearly see that the distance from here to here is it's the same, and you have this like line where it goes through always. That's the D. And phase shift, I covered it in my previous lesson, is if you have your line, you can like shift it left to right, and the phase shift is the C. I'm going to write it in black as well. So let's do an some exercise as well to actually see if you understand what to really do. So it said that the amount of daylight L in hours in London 2024 can be modeled by L is equal to A sin B in the brackets of T minus C brackets end plus D, where A, B, C, D are all more than 0 and T is the day of the year. And I'm not going to read out the example, I hope you can understand. And it said two very important values, that the maximum value L is 16.63 hours a day, and the minimum value, which is over here also given, is 7.83. So right now you can take the time to do it for yourself, but I'm going to start solving it to actually understand. So it's always said that if you want your D, which is this, you can do it very easily. D formula is just the maximum plus minimum divided by 2. So it's 16 plus 63 plus 7.83 divided by 2. So you go to your calculator, you want 16.63 plus 7.83 divided by 2. And then you get your answer to be 12.23. And then A is something much more different. Then you always know that the A is the real or the true value of maximum minus minimum. So your maximum is 16.63 minus 7.83. So you can really, what you can do is just take this, copy paste, enter it as minus, and you will get 4.4. This is your answer. Something very important to mark out: if your answer comes out as negative, then you never write it down, because the A can never be negative. So now it will get definitely more tricky. So what is B? B is the period. And I taught you a very good trick how to actually get the period in easily each time. So if you have your graph that needs to be extended. Right now I extended it pretty good. However, it's just a sketch. And I always told you that you need to get the period, which is P is equal to x2, x1, where all are minimum or maximum. And you have to write both min, also known as minimum, or maximum. So how to do this? Well, you can kind of see that you can extend your graph and you can get your new maximum though over here. And obviously you don't have the coordinates for this, but you know that the y coordinate will be 16 of 63. And now you're wondering, how do I get this? So obviously you're going to kind of do a very easy reasoning that the length from here to here is the exact same. So, and then you have to kind of puzzle out, and then you have to find the distance between this and this. So obviously this is at 356 and this is at 173. And then you have to do 356 minus 173. Then it will be 183. And then obviously this is also 183. So if you want to get this point over here, you will have to add 356 to 183. Isn't that kind of logical? Then you will go 356 plus 183. Then you will get it to be 539 and 16.63. and that's your coordinate. And now you kind of have seen that you have 2 of the maximum points, and the formula for B is that you divide, let's use radians over here because it's not specified, 2 radians divided by the period, and the period is obviously x2 minus x1, where it's the minimum, and then you will get your 2p, and then you will get 539 minus 173. So obviously this will be a very small number, and the trick over here is that you don't have to fully write it out, meaning that you can do your 539 minus 173, and then you will get 366, and then you can just leave it as 2p divided by 366, because if you divide with p it gets messy and there is no need for you to do this, and this is your final answer for your B as well. So let's go to C. Now you might be struggling. So obviously, as I talked before, C is the phase shift, meaning that the graph has been moved from left to right or right to left, and you don't know this. However, this is something very simple, even with, and I even struggle with this, meaning that how you can do this is just replace all the numbers. So let's go to your numerical solver. I really like to use numerical solver for anything that isn't a quadratic or a cubic function, because they have more than one answers. However, you can just plug in your data. That let's use a random coordinate. Let's use the maximum. So you know that your D is 12.23, and now you know that your A is 4.4, your B is 2p over 366, and let's use a coordinate. Let's call the maximum coordinate P, and it will be 173 and also 16.63. You're wondering why I called it P. I just put a random number. However, you take your coordinate, and then it's the same one in your graph, this one, and then you just replace your function, and then you see that L is obviously your y value, and then you will get your function to be 16.63 is equal to 4.4, always check your function, 4.4 sin B sin brackets. Now you will put your 2 pi over 366, and now you have another bracket, and here is t, and you know that the t is the x value, and the x value is your t, it's 173, and your x value is this, because it's a coordinate. This is the y value, this is the x. It's just the t has been x has been replaced by t. So you have 173 minus c, then you have 2 brackets plus d, and d is 12.23. So a lot of you people make a big mistake when putting data in. You see that we have 2 pi. 2 pi means that it's in radian mode. So always when you do calculation with radian or degrees, check, okay, now we're in radian mode, we are safe. And then we go to numerical solver, we put that 16.63 is equal to, let's clear, 4.4 sin brackets 2, where's pi? 2 pi divided by 366, 173 minus x, because we're searching for c, and then plus 12.23. Now you have your function, alpha and sol, and then you get your function. If you have a function that is something like very close to a specific number like 81, 82, 83, or 81.5, you will see that you have two nines as well, and that means that you obviously have to round up, and the C is obviously 81.5, and that's your final answer. And that's everything is correct because it all makes sense. And you can check, but I know everything is correct. And voila. And then one more model that you have to learn before you can go. Logistic models are 9 out of 10 times used for population. So how it works is that let's say you have a species of fish, and the species of fish come into a lake and they start reproducing very fast, and then at one time there just comes a maximum, and the maximum is usually that there is no more room for new fish. So this is the maximum capacity, and you always have to know that the maximum capacity is just L. If someone asks that what is the maximum capacity of the bears in the forest, and you have your L given, then it's obviously L. And also y is equal to L over here as well, to show you that this is the maximum. So your initial value of the population is L is divided by 1 plus C, because obviously if you're looking at the graph, this is time, and y value is population, and therefore you can find the initial population very easily because it is L divided by 1 plus C. And then you can always find the maximum point of growth as well. Some papers can ask you this, and this is something not as important, but I suggest you writing it down in your notebook. It is a natural logarithm of C divided by K is the X point, and the Y point is just L divided by 2. Because obviously this is just in the middle, and then it's natural logarithm of C and K to find the X point. And I think I will do an exam or small exercise from the exams as well for a logistic model as well to make sure you understand. But right now, that's it. Thank you.